Welcome to lesson 1.7. This is reflectional and rotational symmetry. We're going to be talking about a lot of interesting things in this lesson, but I want you to know it is a started lesson, meaning it is not required. You do not have to do this lesson if you do not feel it, but you will take a 0 on your master check, but you can move right on to the test. All right? Well, I suggest seeing if you can handle it. Let's just jump right in. What is rotational symmetry? Rotational symmetry is the amount of degrees you must turn an object so it looks exactly the same. So in our first example, we have a square here, and let's say I'm trying to figure out, does this have rotational symmetry? Can I turn it and make it look exactly the same? Well, let's try. So if I return this, you'll see here, I start here, and if I just turn it a full 90 degrees, this square looks exactly the same. It goes right on top of itself. If I turn it another 90 degrees, it goes right on top of itself. So this does have rotational symmetry, and it's rotational symmetry of 90 degrees. Over here we have a hexagon, meaning it has 6 sides. Let's see if this has rotational symmetry. I'm going to try to turn it, see if I can get it to look right over itself. I'm turning, and not after one full turn, look, it's right over itself. So this does have rotational symmetry, but look, it's kind of hard to figure out how much angle I had to turn it before it mapped onto itself. So you look, not even one full turn, and it carries on to itself. Now, luckily we have a formula to figure this out, all right? And this formula, though, only works for regular polygons. And what a regular polygon is, all right, this only works for regular polygons, and regular polygons mean they have the same lengths for all the sides, and they have the same measures for all the angles. So all the sides are the same and all angles are the same. All right, you should probably write that down. The sides are congruent, remember that word, and the angles are congruent. All the sides and all the angles. So like in a square, it has 4 equal sides, 4 equals angles, and a hexagon has 6 equal sides, 6 equal angles if it is a regular polygon. This formula, though, works for all regular polygons, and all you have to do is take 360 degrees and divide it by n. And by n I mean the number of sides. Okay? So, for example, in this square, if I want to find out the rotational symmetry, you take 360, all right? You divide that by the amount of sides it has. It has 1, 2, 3, 4. And so the rotational symmetry equals 90 degrees. In this case, we have a hexagon, right? So we take 360 and we divide by the amount of sides. It has 6 sides. So we know this has a rotational symmetry of 60 degrees. All right. So if I rotate this 60 degrees, all right, then it carries on to itself. That is rotational symmetry. Let's try 2 more examples of this. We want to know the minimum amount of degrees you must rotate each regular polygon here to carry it on to itself. Well, the first one is a triangle, all right, and that has 3 sides, so all we have to do is take 360 divided by 3, and we would get 120 degrees. So the angle of rotation here is 120. Put that right in the middle. If you look over here, we have a pentagon with 5 sides, so the angle of rotation, all we have to find the angle of rotation that we must spin it. We just take 360 divided by the amount of sides, 1, 2, 3, 4, 5. And when you do that, you should get 72 degrees. All right. So the angle of rotation is 72 degrees for it to map onto itself. Let's try those out. Let's see if you just turn it 120 degrees, it should carry right onto itself. All right. We are going on to non-regular polygons. So that was easy because those are regular and there's a formula. But let's say they're not regular polygons, meaning all the sides and all the angles aren't the same. So if you look at this parallelogram right here, the sides are all different lengths and the angles aren't the same. So to figure this out, you kind of have to use your own eye and figure out how much do I have to rotate this parallelogram for it to carry on to itself. What's its rotational symmetry? Well, just take your paper and try turning it. See how much you have to turn it. If you turn it 90 degrees, that doesn't carry on to itself. But if I do it by 180, it carries on to itself, right? So let's try it again. All right, we're trying to figure this out. So we're going to go 90 doesn't carry onto itself. 180, 2 turns, and it is. So the angle of rotation here, so the angle of rotation to carry it onto itself is 180 degrees. In this one we have a trapezoid, and we're trying to figure out how many degrees we must rotate it to carry it onto itself so it looks exactly the same. Well, let's try it. Go 90 degrees. Nope. We can go 180 degrees. Nope. 270. Nope. And you'll notice here that you have to go all the way around. So this, you have to turn it all the way around to come back to itself, this does not have rotational symmetry. All right? So if you can't turn it, symmetry. So in this case, since we can't turn it less than 360 degrees, you have to turn it all the way around. This does not have rotational symmetry. And not all shapes have it. All right? So it's good to know. Sometimes they don't have it. Now this one is a line of symmetry. The last time we talked about rotations, this is more about a reflection. All right? And a line of symmetry is a line that you could fold the image and have both halves match exactly, right? Like mirror images of itself. All right? So for these two, we're going to draw the line of symmetry that we could fold it and it would carry onto itself. All right? So that's where it's exactly in the middle. Well, on this A, where can I reflect this so it looks exactly the same on both sides? Would it be here? All right. Say I reflected it over here. Would this be cutting it exactly in half? Well, this top half does not look like this bottom half, right? So this is not a line of symmetry. But I could draw it right down the middle over here. And if you look at this half, is exactly the same as this half, okay? Same. So that is our line of symmetry. All right. That carries this object onto itself. It's right down the middle. Now for this square, this one has a few more actually. So where can we draw lines so it is exactly cut in half? Well, we have a line of symmetry right here, right? Both halves are exactly the same. We can have a line of symmetry right here where both lines are exactly the same. And you might say, oh, that's it, there's only two. Well, there's actually more, right? I could actually cut it right down the middle over here and it would be exactly the same if I folded it over. And if I folded it over here, it would be exactly the same. So a square actually has 4 different lines of symmetry, whereas this A only had 1. All right, now that we know that, we call this reflectional symmetry, where we can reflect it and it looks exactly the same. Well, we're going to try to do that on a coordinate plane. So we're going to draw all the lines of symmetry on these, and then we're going to state the reflection that would carry the figure onto themselves, right? So where can I reflect it so it looks exactly the same? So first we draw the line of symmetry. In this triangle, where can we draw that cuts exactly in half? Well, there's only one, and that would be right down the middle right here. All right, that would be our line of symmetry, right? And both sides look exactly the same. Well, what is the equation of this line right here? So if I reflected this triangle, it would still look exactly the same. Well, you might remember this from the lesson before, but this would be x equals, and let's see, 1, 2, 3, 4, 5. So at x equals 5, there's a line of symmetry that maps it right onto itself. All right, it carries it onto itself. So in this rectangle, all right, this is not a square, it's a rectangle. Where can we reflect this so it looks exactly the same after we reflect it? Or in other words, carries it onto itself. Well, we have one right here, right, that cuts it right down the middle. All right, and we also have another one. We have 2 here, where if we drew it here, it would cut it right down the middle. So this has 2 lines of symmetry that would carry it onto itself. All right. The first one is at x equals -1, 2, 3, 4, 5. So x equals -5. Or there's another one. We have this guy right here, which is y equals 1, 2, 3, 4. Remember, horizontal lines are y equals. We're applying all our knowledge here. y equals 4. So it's really important that when you do these, you draw the lines of symmetry first, and then you state all the lines that can carry these objects onto themselves. And that's it. That's the challenge lesson for you. Good luck. Good luck. Good luck. Good luck.